Editing in diffusion models has kind of not been a very big thing. Like, it doesn't really work very well. In GANs, it's pretty easy because you have a map directly from your latents directly to your output image, and that's just your generator. And that's just one function. Uh, your image is equal to g of L. And that's just like some complex function. But it's easy to manipulate because it's just one function. Now, a diffusion model, on the other hand, requires multiple functions, essentially, because you're passing it through the model multiple times, and the model is conditioned on the time step. So basically, it requires multiple functions to get your output image. And that's quite annoying to deal with. So this hasn't really been done very well before. This paper does a unsupervised method to do that. So essentially, they are just looking for like directions that change the image in an intuitive way, instead of finding a direction that they want to change and then changing it in that way. But like this is the first step, and it does a pretty good job with it. And I think the theory behind it is kind of cool. This image kind of shows that. So if we start here, that's the start. That's the dog. Um, you want to move along this image manifold. So this is going to be in terms of it's like a topological perspective, a differential geometry perspective, and basically you have this manifold chi in which your images basically live on, and you want to move along chi in a way where you basically follow a trajectory towards some desired change. So if we move along this way to the right, then it produces this yellow one, so it produces this dog. And if you go along the left, then it produces this dog here. And they also show that this isn't just random. The directions they find actually correspond to things. It corresponds to like a change like this. So yeah, that's the idea. And I like this image because it shows that you have this noise and you're moving along this manifold in the noise, and you just decode it, and you end up on like a different part um, somewhere up here, and that's your image. So you can still move along this path here if you really wanted to, but it doesn't change very much. Um, so yeah, that's the idea. Basically, you want to change chi, and according to some metric. So to do that, um, basically this image has everything in it. Um, I'm going to kind of draw it out over here. Um, so to start, let's say we have a manifold. So this is chi, and this is going to be where our images live on. Now, chi is basically, so you have your UNet, and your UNet, it looks like this kind of, you have some convolution, you then downsample, and then you have another convolution, and then you downsample again, and then you have some middle block, and then you upsample, and you have another convolution, and so on. This is what it looks like, and the output will be your noise. It'll be epsilon. Now, what they look at, or what they notice, they didn't actually notice this, but H defined by the bottleneck layer of the UNIC exhibits local linearity. So this part here exhibits local linearity, and that's going to be useful in their implementation, in how they edit these images. So we have this manifold here, chi. So chi is just our image at some time step, and this works for arbitrary time steps. So the time step doesn't matter. Just think of this, well, the time step does matter, but the method works for an arbitrary time step. The time step, there's a little variation on the time step, but it's just our image at some time step going into the diffusion model. So this is just the input, our noisy image. and h is going to be our intermediate part at the bottom of the unit. So that's the setup. Now, the problem with chi is we actually don't know what this manifold looks like. This is what we're trying to approximate with our model. Our model is trying to learn this. However, we do know this part here, mostly. If you have, so this, you can think of this top part here, this part right here, as being a function f, and f is a mapping from the chi manifold to your latent manifold, h, so chi to h. And this basically defines a second manifold. That looks like, it doesn't look like that. This is actually super high dimensional, but it'd be two dimensional. And basically this defines, it defines a mapping between the two. So if we have a point here, so this is a point x in chi, and this point can be mapped somewhere here, somewhere on this manifold using f. And I just show that it's like really far away to show that there isn't an ease. It's somewhere kind of arbitrary on the manifold. I'm gonna draw it up here, but yeah, it's basically you can define this mapping, and that's f. F is our U-net encoder. Okay, so now we have a mapping from this space to this space. Why is that useful? So later we're gonna they show that this is a like spherical manifold, which is annoying to kind of use. It's kind of annoying to manipulate because it's spherical. It's not flat. However, h is also not flat, but it exhibits local linearity, which is very nice. So like if you look at this manifold, it may have some curvature, but like if I draw like a massive curve like this, and then I zoom in a lot, it looks flat at this point. So it exhibits local curvature, this here. However, it's not. It exhibits local linearity. However, it's globally curved. But local linearity allows you to manipulate this manifold or manipulate this point on the manifold and manipulate it in a way like it's a Euclidean plane. So you basically treat it like it's on a linear surface. And linearity is awesome just in general. There's so many nice properties. We know how to easily manipulate linear surfaces. We don't know how to easily manipulate curved surfaces. So yeah. Now, the nice thing about that is you can also define a map basically saying if I'm changing in h, how does that change chi? So remember, we want to change this point in some way so that we move in a desired direction. So if we are changing in h, we want to know how that affects chi, because chi is x and chi is inevitably what we want to change. This point x is what we want to change. We just have a mapping to h, which is a nice space. So we can define we can take the Jacobian and let me draw this. So we can take the Jacobian jxv. So this basically represents jxh. So if we have, if we take the Jacobian of h, so of this point here, with respect to like this space here, basically this tells us how, like if we move in h, how does that change x, basically? So it's very nice, and you can get this. So this is pretty easy to get. You just get that by differentiating f here. So you can get this. You can get this mapping. Basically, if I'm changing in h, how does that affect x? How does that affect my change in x? And it defines this very nice property. And they say that up here. Let me change my highlighter. So the linear map can be described by the Jacobian, which determines how a vector v is mapped to a vector u. So they define this in terms of tangent spaces. So if you have a tangent space here, and basically a tangent space is if I have a point, like what are like all the vectors, all the what are all the tangent vectors here? So yeah, basically they define a tangent space here, which you can get from the Jacobian. And you're basically like if you have a tangent space here, you kind of like paste that onto here. So like this tangent space defines some set of gradients here. It defines your gradients here. So in like some high dimensional space, it defines that. So basically, this defines how you're changing, like this how you can change in X. I guess it can define the curvature and all of that. It defines the gradients at this point, which you kind of like paste onto here. So it's not this space here or this tangent space here, which H. This would be X. So you can kind of this Jacobian here basically pastes this onto this point here. So if I move in H, how does that change chi? And you do that by JXV using automatic differentiation in the unit. So if this was a vector, let's say U, I think this was U. No, V. If this was a vector V, you can map it to here. Maybe it looks like that for some reason, and that would be U. So you're basically defining these tangent vectors from one space to another, from your bad space that you don't know to the space that you do know. So how does a change in H kind of affect, how does that change X? If I move a little bit here, how do I move here? Essentially, that's what you're looking at. So yeah, they define this nice idea, and then basically you have a metric for this space because the space is Euclidean. The distance between these 2 points is the Euclidean distance between these 2 points. So it's basically the Euclidean distance. So that's easy. We don't know the distance here, and we want to define a distance metric here so that you can kind of move in a nice way. You know where you're going. So if we have a distance metric here, they say if a smooth map exists between the original metric of unavailable space, so we don't have a metric here, and a metric available space, we do have a metric here because it's locally Euclidean. The pullback metric of the mapped space is used to measure the distance in the original space. So the pullback metric, that's what they're defining, or there exists this metric called the pullback metric, and it basically allows you to define a distance metric here in terms of distances here. So, and the reason you want that is because if you can define a distance metric, you basically know a lot about the manifold. You know at least you know a lot about it locally if you can define a distance metric locally, because you define it locally here. So locally, you have a lot of information if you have the distance metric. You can do a lot with it. You can define the distance between 2 points, and that allows you to do a lot. It allows you to move in kind of a known way. So they define the distance metric. Erase this. Yeah. So distance metric here, pullback metric is pretty simple. So if we have this mapping V, so we map some vector V in this space to the vector U here, which are just like you can get the point back from that, but it basically tells you how you're changing your tangent vectors. They basically, so you want to get the distance of, or the distance, the magnitude. If you have the magnitude, you have the distance. The magnitude of a vector in X or in chi, and they define that as the magnitude of a vector here. So like they're equivalent because there's an equivalent mapping F. Now we basically want to map this back. So this becomes, we know that U is equal to JXV. That is here. So we know that. That's just our Jacobian. If this is, yeah, that's just our Jacobian telling us how we change. And you can just replace that. So we know that this is U transpose. This is equivalent to the U transpose is a like a vectorized way of kind of showing the Euclidean distance. And then you can just define this as JXV. Maybe it was transposed. One of them is transposed. That's what matters. JXV. As long as it gives you a scalar and not an outer product. And then you can just rearrange this to give you V transpose JX, JX transpose JXV. So basically you're saying, I know the distance here, the distance is Euclidean, and I know a mapping back to, or I can define a mapping back to it because I know the mapping forward. So this is basically your mapping from V, and you can basically say, if I change, like what are the distances here? And that defines a distance over here. So that's the idea. It's pretty, it's not too bad. It's just, if I move here, you can define the pullback distance, and it basically tells you how you move in the original manifold. So yeah, because you have this equivalence mapping telling you if I change in H, how do I change in chi? So that's the idea. But now we have a metric. And because we have a metric, that means that we can move along this really nice Euclidean plane here. We can move along this Euclidean plane, and we know where we're going to get to. Like if I kind of have a curved surface here, if I kind of move along it, I don't really know where I'm going to end up, so I'll end up somewhere down here. But if I have a smooth surface and I step along it, then I know I'm going to end up right here, because not a smooth surface. If I have a flat surface, then I know where I'm going to end up. So it's you have basically a deterministic direction you're going to. So now we have a mapping. Now we can move in H and map it back to chi, and that is basically what we want. That's what we were looking for, because now we have a mapping backwards, which is looks like this, and that's just our pullback metric. So we now have a mapping. Now the second part is they basically want to find, so this is the unsupervised part. We have this mapping. That was a very important part. Now they define this over here, and they just want to find latent directions with a lot of semantic meaning. So semantic latent directions. And basically, using the pullback metric, they can extract semantic directions V. So basically, directions in here on the original manifold that have large variability of the corresponding vector in U over here. And they find a unit vector V that maximizes V. So basically just what vector maximizes the distance here, or the norm here. And you say by maximizing the norm, or remaining orthogonal to V1, so assuming you found vector V1, you can find a second vector. And this process can repeatedly have n semantic directions in chi. So basically, you have this really, really high dimensional space. The number of dimensions is equal to the number of parameters here, so maybe 100,000. And they basically want to find high variability directions. Basically, if you know PCA, it's basically that. So you find vectors that explain most of the space. So yeah, tablet's going to die. That's fine. But yeah, you explain most of the variability at that point. So it's basically just PCA. So they find it was 50 vectors that basically make up the 50 principal components to explain the variability of that, of this point, instead of 100,000. And that's also why one note they bring up is they can't actually compute the Jacobian. They approximate it. So, however, since the Jacobian of too many parameters is not tractable, we use a sum pooled feature map, which is just, it's basically the Jacobian. And they just use Jacobian. So basically, you want to find these feature directions that have a lot of variability. They explain a lot of the variability. So maximizes the L2 norm, or not L2 norm, maximizes the pullback norm. Here, so I mean, here you can't really visualize it because there's 2 dimensions, but in the 100,000 dimensional space, 50 vectors, like 1 is going to, there's a lot of variability. So that's the idea. And that's kind of their second step. So this was kind of the first step. It was defining a distance, and their second step is basically getting principal components. And that's at the point. So it's getting principal components here. And they do that by getting the first eigenvector. And the first if you know the eigenvectors and that all the matrix stuff, then like the first eigenvector is the one associated with the largest eigenvalue. So and you just take the top n vectors of that. Yeah, 50. So that is the second step, and that's just defining like directions they want to move in, because it's unsupervised. So you may want to find a direction that, I don't know, turns a dog into a cat, but you need to do that. They don't have a method to do that. This is an unsupervised way. They basically find directions with high variability, and then they look at those directions afterwards, and then they say, oh, this direction had a change in this way. So they don't define a direction going this way. They basically just find a direction going this way. They don't themselves find it, which is kind of, but you got to start somewhere. So hopefully in the future that'll change. Yeah, so they basically just find a bunch of vectors. That's it. And yeah, it's just an approximation of the original space. So iterative editing. So now that you have this vector, so you know which vector, you know which direction you kind of want to move in, because of this PCA that they did, this PCA-like thing that they did, you can now edit your point. You want to edit this point over here, and you do that by editing this point over here. So to edit it, over here. So step 3 is basically editing. So moving in Chi, that's basically step 3. And you can define the movement, so the update, as x is equal to x prime plus some gamma, which is basically your step size, times vi. So if I have a point x and I have a direction I want to move in, then I just update it by taking a step along that vector with some step size. Yeah, pretty simple, but the way you have to do that is you have to do that using what they call parallel transport. So they edit a sample, it's a sample using that formula, where gamma is a hyperparameter, that's the size of editing. However, it does not work because vi, which is the on Chi, may escape the tangent space at that point, or it may escape the tangent space. So it's necessary to relocate the direction to a new tangent space. To achieve this, we use parallel transport that projects vi onto a new tangent space. Yeah, so basically that's multiple editing. So I like this picture up here. So basically to edit a point, erase this. Yeah, just erase all this. So if basically to edit a point, so we have a point here, you basically map it to h. So you map it to h, and since we have a metric that tells us how we can map back, the pullback metric, then we can. So you then define the plane here, which tells you how you're changing in h with respect to x. And you pick a direction with high variability, and you move along that direction. So you just take a step here instead of on here, because this, remember, this is flat, and we like taking a step on flat surfaces. Then you map this back, or you map the vector back, and you can take the step there. But since this was flat here, but you basically want to change multiple times, so taking one step isn't going to be enough usually. You basically want to take a step down this manifold here. So you know that taking this step here is, you know where you're going to end up on H, which basically means you know where you're going to end up in X because you have this parallel mapping. However, if you were to just say, okay, I'm going to go in this direction over and over and over again, this one's actually, it would actually go like that, then you notice a problem here. We actually want to go along this curvature here. And the problem is because this is locally Euclidean. However, it's not globally Euclidean. It's not globally flat. So we basically have to, once we map back and take the step here in X, or in chi, then once it's updated, you can't just map back, or you can't just take the step in the same direction according to this vector you found in H. You have to map back to H, and you have to update your vector to be something different. So you can't just take this step here, the orange step. I'll make this like purple or something. You can't just take this orange step here, which was your old step. You can't just like smack that on over here because it's the Euclidean space. It's only local to this point here, but you can see it changes over here. The space doesn't look like that anymore. It's now changed. So you basically map back to H. You do the same process where you find this vector, and then you update X using the distance metric, and you do this again. So basically, you're just hopping back and forth, looking for a vector in H, and then jumping in that direction. And you do that repeatedly until you're satisfied with where you end up. And that's what they do over here. And that's, yeah, you can kind of see it kind of takes like a walk on chi. And you do that using H. So that's the idea, and they do that using geodesic shooting, which is basically the idea described there. And they need parallel transport for that. So yeah, basically parallel transport is just that. The first step is you basically convert VI in chi, or in the tangent space of X, actually, to UI in, it's not H, but it's a tangent space of H, by U is equal to JXV. And then you basically update by H is H prime, which equals H plus delta UI. So you're just taking the step on H instead because you know how taking a step on H works, and then you just map back. Map back to chi. So that's it. And the reason you need to project back is because it's like you do this again and again, but you can't just do this step over and over again. You can't just map to H once and then kind of move along this. You have to map back and forth between the two. Yeah, so that's geodesic shooting. Global semantic directions. So this idea is cool. So however, the semantic latent directions are local. So the semantic latent directions they find are very local. It's not that useful. It can be useful, but it's not as useful as if you found a global latent direction. Like if I wanted to make something maybe more red, maybe I wanted to make a picture more red, then I can find a global direction to do that. Yeah, so it's only local to individual samples xt. Thus, we need to obtain a global direction for every sample. So to do that, it's easy. they define a global semantic direction by averaging the closest latent directions h of individual samples. The global direction can be used to edit any sample x. So yeah, it's just averaging a bunch of directions in h. So you have a bunch of these directions up here. Maybe I have a point here. Like maybe red is over here. Like this, there's this part of the manifold over here that I want to move towards that basically tells me, or like a direction that I can move towards that basically tells me, or that makes my image more red. Then there would be a vector here at this point pointing there, and a vector here pointing over there, and the average vector would be like that. So you just take a bunch of points, you average the vector moving in that direction, and that's how you get it, that global direction. Yeah, easy idea for that. Just average the closest latent directions in H of input samples xt. So not bad. Oh, one cool thing they find is they compare eigenvalue spectra between different t. So this is where the value of t actually matters. So if I were to tell you this, and I were to tell you that you can edit an image, you may think that it probably actually does depend on t. At the beginning, I kind of said it didn't, but it actually does depend on the time step. Where are you at in your diffusion process? And the reason it does is because imagine I'm basically at time step 0, and I basically have a picture of a dog. At that time step, if I try to edit the image, it feels like it's going to be hard intuitively. And if I'm at a very noisy time step at one of the beginning time steps, it feels like I could easily edit that image. I could easily add a little bit of noise, and it would significantly change the image because there's not any of the image there yet. It's just noise. So that's what it feels like, and intuition is right this time. They become flatter as t is closer to 0. This shows that a few dominant feature directions exist for xt, whereas diverse feature directions exist for xt for small t. So yeah, that's so the idea is basically there's a few dominant feature directions in xt. Oh, never mind. T is the... I was wrong about that. Yeah, so big T is your... intuition was not right. So a few dominant feature directions for x big T, while a lot of diverse feature directions for x small t. So I think that's how they define it. Yeah. All right. So never mind. I'm wrong about that. So whenever you're at x at time step 0, there's a lot of diverse directions you can move in because I guess the image is already formed. So maybe you can change a lot of the different features about that. Maybe since there's already a picture of a dog there, you can kind of change the eye color or something like that. While it has like everything's kind of the same at large t. So at the beginning of your diffusion process. So I was wrong about that. Intuition for me was not right. So that's an interesting find, that there's a lot of diverse feature directions at small t. They also say they have to normalize it. So the editing signal of VI is propagated and amplified through the denoising process. The amplification may lead to unexpected artifacts whenever you generate X0. So basically, you just need to normalize this so that like the editing effects don't get amplified and they look weird. Yeah, and we can see some of these editings here. So these directions basically find the high variability directions, and then they change it. So this is the image, and then they move in some direction. So 0.5 t is just in the middle of the diffusion chain, and this is at the very beginning. So yeah, they find this direction, this direction, this direction, and it does a pretty good job. Like it doesn't look bad. The outputs, they look pretty good. Like it looks pretty good, and yeah, they find these directions. It changes some color. But the attributes are manually interpreted because the directions are not supervised. So they basically move in some direction and it outputs some image. Now, you may think, okay, I'm just going to move in some random direction. They show that moving in a random direction does not result in something nice. So yeah, like if I move in a random direction, then it doesn't do anything. So the directions they're finding do actually mean something. So this direction here would actually represent like moving towards a black dog as opposed to like a brown dog. And these are the global semantic directions. So yeah, it looks like black. So they choose, there's this direction black, and they find this global direction. And yeah, you can see for two different images, it makes it more black. Yeah, different pose, young, so makes him young, and furry. So the global directions also look nice. I'm curious if this just has to do with the dogs, or like if you apply this to something really strange, like a plant or something like that, what that would do. But the global directions do actually make sense, at least for the dog or the human part of the manifold. The global directions do actually work. Now, one last thing is I said that chi was spherical. And they find this by basically, so they say chi is a curved manifold, and they use the geodesic metric to kind of figure that out. So to define the curviness of a line segment, x1, x2. So basically you have these 2 points along your manifold here. And you have some line segment here. What's the curve? How curved is that? It's basically the angle of the two spaces centered at h1, h2. So using the corresponding mapping over here. So this is just the angle of the tangent planes, so or of the tangent vectors there. So like you have or the tangent space. So you have this tangent space here, and you have the tangent space here, and it's the one in H. So it'd be these two here. And you basically want to look at the magnitude of the principal angles. So remember that they take the principal components for high variability. They just use those and look at the magnitude of the angles between those. It's kind of hard to show in 2 dimensions, but you can imagine if I have 2 points here, this would have like a zero angle. But if I have, say, this point, it would have it has an angle. I guess this would be negative some theta, or this would be some theta value, some angle value. That's kind of negative. So the idea is if there's a high angle, then there's high curvature, or if there's a high, basically magnitude of the k principal angles, then there's higher curvature. And this is useful because if we look here, yeah, so that's just the metric. If we look here, lerp, slurp, weird names, but lerp is a linear path, slurp is a spherical path. You can see that it's curved in the linear path, but flat in the spherical path, basically meaning that the surface is curved. And since it starts here and it ends here, basically you can kind of think of that as going from one side of the sphere to another. So that's kind of the idea. And they show that it is spherical, and the geodesic is flat. So yeah, basically looking at the angles, you can tell like visually here, if I go from this point to this point, then lerp, like it has this curvature here, while slurp would be flat. So because it's spherical, it's mapping on spherical. Yeah, so they show that, which is pretty cool, that the input chi, the manifold chi, is spherical. However, that's spherical in like a really high dimensional space. So this sphere here is not what that sphere is going to look like. It is spherical. It's curved. Yeah. So that's what they say. The curved manifold. Yeah. That was another cool thing they thought they showed. And then they have some more examples here. If you're interested, go ahead and take a look at them. They have some proofs at the end. But it looks pretty good overall. The method. It would just be cool if so you got to start somewhere, but I think it would be very interesting if you can define your own directions according to something that you want to see. It also works with stable diffusion, this method. So yeah, this is stable diffusion. So stable diffusion is latent diffusion. They worked with pixel diffusion, and it also works with latent diffusion. So they find like a direction Van Gogh and Cyberpunk City, and it looks like it works with that pretty well. Also with global semantic direction for zoom out. So yeah, it zooms out. But that is the paper. I really like this paper. It kind of shows like some intuition behind how diffusion models actually work, which there is none right now. So yeah, kind of a first step towards that.